Today we're going to talk about graphs that represent situations. So our warm-up question today is about a jumping frog. The height in inches of a frog's jump is modeled by the equation h of t equals 60t minus 75t squared, where the time t after it jumped is measured in seconds. So find h of 0 and h of 8/10. What do these values mean in terms of the frog's jump? So what I want us to think about, if we're thinking about a frog jumping, it's going to be here, it's jumping up, and then it's landing back down. So if you're looking at this, we're finding h of 0, that means that we're going to evaluate, we're substituting 0 in for both of those t's, and 60 times 0 is 0, and 0 squared is 0. So this whole thing is going to be 0, okay? So if we find h of 8/10, and you do those calculations as well, doing the same thing where you're evaluating. So here, I'll even show this. Whoops, that would be 0 squared. That all equals 0. So if you're evaluating this for 8/10, and you do the math of that, you're also going to get 0. Okay, so you can use a calculator for that. So what does this mean? So the frog is on the ground when t equals 0 and t equals 8/10, okay? Because this y value, or the h of t value, is the height, and that tells us that it's back on the ground. So it says how much time after it jumped did the frog reach its maximum height. So if we're here, if this is 0 seconds and this is 0.8 or 8/10 of a second, remember we've talked about that the vertex is halfway in between those at this point. And so if we're halfway between 0 and 8/10, it would be 4/10, okay? So we know this because it's the halfway point of the jump, okay? All right, our next piece is a catapulted pumpkin. So the equation h equals 2 plus 23 7/10 t minus 4 9/10 t squared represents the height of a pumpkin that is catapulted up in the air as a function of the time t in seconds. The height is measured in meters above the ground. The pumpkin is shot up at a vertical velocity of 23 7/10 meters per second. So without writing anything down, we want to consider these questions. What do you think the 2 in this equation stands for? So remember what we've talked about. This here, that does not have any sort of variable with it, is going to be our starting height. So this means that the pumpkin was launched from 2 feet off the ground. What about the negative 4 9/10 t squared? Earlier this week, when we were dealing with these types of questions, we saw minus 16 t squared. That's representing something in feet. Here, if you notice, we're talking about meters, okay? Everything else is talking about meters. So this negative 4 9/10 t squared is the same effect of gravity, just in meters, converted to meters as opposed to in feet. If we graph the equation, will it open upward or downward? So remember, for this, we're looking for the quadratic term to determine if that is positive or negative. So in our equation here, our 4.9 t squared is negative, so it's going to open downward. Where do you think the vertical intercept of this will be? So that's where remember the vertical intercept is going to be on the y-axis. So this here is vertical. So we're starting at 0, 2, because we started 2 feet off the ground. What about the horizontal intercepts? Well, it's starting here at 2 feet. We know the pumpkin's going to go up and come back down somewhere, but we're not exactly sure where that is. Just looking at the equation in standard form doesn't make that easy. If we are in vertex form though, sorry, not the vertex form, if we're in factored form, that could help us easily tell, or more easily tell, what it's going to be, okay? So then we're going to graph this function. So I went ahead and typed it in, and you can use h of t equals, that's fine, it only said h equals. If you don't want to use that, you could just use x's, and you don't actually have to put the h equals either. So I have this typed in here. We can't quite see everything, so instead of just moving it around, let's change our window here. Okay, so we're good on the x's. Let's change the y's so that we can see a little bit higher. So there we go. Now we can see everything. We can actually see more than we need because we don't need, you know, we don't need the or the negatives anywhere here because that doesn't make sense in this situation. Okay. So based on our graph, let me move that out of the way for a moment. Based on our graph, we want to actually find what the vertical and horizontal intercepts are looking at this graph. Okay, and then we're going to explain what each point means. So the vertical, remember that just means that you're looking for the y-intercept. We already said that was the point 0.02. So remember that means that at time 0, the pumpkin is 2 feet above the ground. That's where it was launched. The horizontal intercepts, remember that just means that you're on the x-axis. So if we're, let me get rid of that. If we're on the x-axis, now our first one is happening over here, but does that make sense in this situation? No, because it's a negative. So the only one that we care about is the 4 92/100 0. And what does that mean? That the pumpkin was in the air for approximately almost 5 seconds. Okay, not quite. And then it does ask us to find the vertex. Okay, which is up here. So that vertex is 2.418 and then 30.658. And you could round those if you wanted, or just leave them alone. So what does this mean? That after about almost 2.5 seconds, that the pumpkin was a little over 30.5 meters in the air. Okay. All right. Last piece of information that we're going to deal with says the flight of 2 baseballs. So here's the graph that represents the height of baseball h in feet as a function of time t in seconds after it was hit by player A. So this is all player A's information. So we're going to call this function f. Okay. The function g, defined by g of t equals the quantity negative 16t minus 1 times the quantity t minus 4, also represents the height in feet of a baseball t seconds after it was hit by player B. Without graphing g, answer the following questions and explain or show how you know. So with this, which player's baseball stayed in flight longer? Okay, so player A hit the ball and then it landed on the ground shortly after 5 seconds. Player B, if we solve both of these things, so this would be negative 1/16 of a second, which doesn't make sense here. And then this is 4 seconds. So which player's baseball stayed longer? So that would be player A. Second question says which player's baseball reached a greater maximum height? So for this, at the graph for player A, this maximum is just over 100 feet. We're not exactly sure what that is. If we know that player B had zeros at approximately 0 and 4, then then the vertex of that would be halfway in between it. So for player B, so I'll do some work over here. So player B, the max is at t equals 2. So at 2 seconds, okay, their ball would be at the maximum. What that means, then we have to evaluate their functions. So if we substitute 2 in there for our seconds, our time, and we do that math, we get 66 feet, which means that player A, again, their baseball would reach a greater maximum height. And it says, how can you find the height at which each baseball was hit? So for player A, up here in the graph, we can just look at the y-intercept. Okay, we can look at the y-intercept. You could also call that the vertical intercept if you want. For player B, all we have is player B's equation, but what do we know about the height, the y-intercept that it started at? We would be able to plug in 0 for time, okay? So today was all about just being able to compare things graphically and algebraically with the equations and things of that nature, and that's it.